You can't fill it in. If it's 3 with a half a page of calculations, then and then 1 page of picture, then it's not going to cut it. Is that 3 written pages, single spaced? Then that might cut it.
Not single space.
Or is that 3 double spaced pages?
No, single space.
Single spaced pages. Yeah, that might cut. And 3 plus calculations or 3 including calculations?
3 including calculations.
I don't know.
Okay, I can. Okay.
Yeah, I don't know if that's going to cut it. They say that 5 pages is a short paper.
So like 4 would be pretty decent.
Yeah. 4 would be pretty decent. But there's so much you can just add in. I can't believe if you're getting stuck because trying to fill in pages, because you could start talking about, what can you start talking about?
Errors. Errors, like experimental errors.
Yeah, not just that, but you can also start talking about what? What's tough is, and maybe later on, this might be tough for you as well, is when they limit the number of pages. They say you cannot exceed this many words. Then it becomes tough because you have to condense everything and say it in a more compact fashion. But, you could ramble on about what? Like Lewis acid-base reaction. This is called a Lewis base. What do Lewis bases do? Here are some examples of Lewis bases. In this reaction, we're using this Lewis base, which is, and all of a sudden you're at half a page just talking about, half a page double space talking about just Lewis bases in general. You could talk about Lewis acids, right? So a lot of stuff you could actually end up including in the report, which would, enhance the report, although not totally. A lot of people think, well, I'm not supposed to talk about that because I just want to talk directly about what exactly happened. No, you could have some background information about this type of stuff. Other things as well. I don't want to give too many hints away, but this is why I tried to give you ideas at the beginning. If you go back and look at the video or something of the presentation, how much time did I waste, although it's not a waste of time, talking about the hazards of, MSDS, this kind of stuff. I'll tell you, in the rough drafts, how many people talked about that? Very few. But of course you can add that into your report, take up pages. So if you're ever worried about not having enough pages, it's pretty easy to fill that. Just go back and look at, the stuff I talked about will easily fill, I think, 5 pages. So that's due on Thursday, but I've already had a request to turn it in Friday, but Friday, under my door. Let's see. Any other questions? So I have Thursday night to work on it.
Did we finish chapter 19?
Yes. We finished chapter 19, now we're into chapter 20. we concluded chapter 19 with just a review of all the basic calculations in chapter 19. We did them all, pretty much. There's a couple of small variations to those.
Yeah.
You can look in the homework. Okay, if there are no other questions, then let's continue on with chapter 20. In chapter 20, we're going to draw the battery or voltaic cell, and we have a wire. And normally the arrangement is you could put the anode or cathode on either side, but we like to put the anode, or I like to put the anode on which side? The left side or the right side?
Left.
On the left side, yeah. You should get in the habit of always drawing it the same way. It makes your life a little bit easier. So, it doesn't have to be on the left side, but just by convention, let's put it on the left side. And then we'll put the cathode on the right side. Which way do the electrons travel through the wire? Do they go from left to right or right to left?
Right to left.
Right to left? It could go right to, it just depends on what side of the table you're on, right? But since we want to always do it the same way each time, we're going to draw from left to right. And so it's going to go from anode to cathode. So electrons travel this way through the wire. That means what generates the electrons? The anode or the cathode is where we generate the electrons?
The anode.
The anode. And we're going to consume the electrons at the cathode. Now, how are the electrons generated? Well, the electrons are generated by, having something pull the electrons through the wire. What's pulling the electrons through the wire? Well, the oxidizer is pulling the electrons. And so some people say the cation pulls the electrons through the wire, like copper-2 ions. But does it have to be a cation? Can an anion pull the electrons through the copper wire? Yeah, give me an example of an anion that would pull the electrons away from the anode to the cathode. Can you think of an anion that would actually, it doesn't make sense because why would an anion want electrons? An anion already has a negative charge. Why does it want an electron? So we need some kind of oxidizer. And so oxidizers can be like copper-2. So cations might be oxidizers. Can a neutral element be an oxidizer? And so what we need to do is we need to go back and take a look at the redox chart and refamiliarize ourselves with the redox chart. Can you name some oxidizers for me? What oxidizers can you remember from this?
Ozone.
Ozone's an oxidizer. So we could bubble ozone gas in here, and that would pull electrons. That's a neutral element. What else is an oxidizer?
O2.
O2? O2 is a great oxidizer. We could bubble O2 gas that will pull electrons through. O2 with H+.
What's permanganate?
Permanganate. Permanganate is a great oxidizer. Should we use permanganate? Yeah, let's use permanganate. Why would permanganate want an electron? It's already got an extra electron. So we'll use an oxidizer like permanganate. just for variety. But is permanganate a very good oxidizer? I mean, it seems to have an extra electron, probably doesn't need. One of the things, you know, at UCSB and UCLA and Santa Barbara City College, is in general chemistry tends to emphasize the physics, doing the calculations like the Bohr equation or this or that, frequency, wavelength, delta H. But sometimes at the expense of just general chemical knowledge, you know. And so permanganate, yes, permanganate is a very powerful oxidizer. This is very dangerous stuff. It's an extremely powerful oxidizer. Why? And so when we're trying to understand chemistry, we try to understand the properties based on the composition, but not just on the composition alone, but also on the, well, structure. Yeah. And so rather than looking at the composition as a whole, we look at the structure atom by atom. And when we look at it atom by atom, we'll see that manganese is not terribly happy in here. Why is manganese not terribly happy? You know, if I use permanganate rather than chlorate, you know, it could have been a violent reaction. Oh, actually, no, I didn't do that reaction, did I? Yeah. If I use permanganate instead of oxygen, it could have been a very violent reaction. It's because when we look at properties, we want to understand the properties based on composition and structure. Do you guys remember that? It's a good time to go back because somebody was asking me about the final exam this morning, so it got me thinking, you know, maybe it's a good time to go back because I talked about that the first week. Properties being correlated with composition and structure. And therefore, this was a question I was going to put on the last quiz, but I eliminated it. But now I think maybe I should have kept it on there. The question was going to be something like this, you know. In the first step of the acid-catalyzed formic acid decomposition, the strong acid reacts with formic acid. In other words, we get an acid plus acid reaction. Strong acid plus formic acid. True or false? So an acid reacts with an acid in the first step of the formic acid decomposition. So the reason I was thinking about it is because, you know, I was thinking maybe some people will think an acid plus an acid, there should be no reaction because both want to do the same thing. Both want to donate a proton, right? So one acid says, here, take my proton. The other acid says, here, take my proton. I insist, you know? So which acid's going to win? Both want to give up protons. None wants to take protons. And so it should be no reaction. So we had stuff like this. Strong acid plus a weak acid. Strong acid plus a weak acid mixture, the pH is dominated by the strong acid. But, you know, the strong acid and the weak acid, do they react? And so now we're taking strong acid and mixing with a weak acid, formic acid. Do we get a reaction, or is it just a strong acid, weak acid mixture? Do we get a reaction?
I think so, yeah.
Yeah, we got a reaction. So how does an acid react with an acid if both want to do the same thing? So how does an acid react with an acid? An acid is defined as a proton donor, right? So if both want to donate a proton, who's going to accept? The weak one? The weak one's forced to accept a proton? So here's formic acid. H, well, let me write it like this. HCOOH. The weak one, you must accept the proton. We're going to form HCOOH2 plus. The weak one has accepted the proton. Yes? Because the weak one's going to be forced to take on the proton. And then we try to draw the Lewis structure of this. Have you tried to draw the Lewis structure of this? Where does that extra proton, how is that going to bond? Well, this is why we want to understand things in terms of structure. And so one way, yes, actually it does. It does react. But we don't call both of these the acid. One is actually going to be the base. Which one's going to be the base? Formic acid. Formic acid is the base. Base is proton acceptor. So formic acid is actually the base. And so what we do is we look at it structurally to see what's happening here. And so if we're just looking at, this being an anion, that's wrong. We got to look at it atom by atom. When we look at atom by atom, we see that manganese is +7. Manganese +7, that is really electron poor. And so it makes permanganate an extremely powerful oxidizer. And so permanganate's a great oxidizer, but I need something else. What else do I need if I'm going to use permanganate as the oxidizer? Actually, I'm going to skip this chart. This chart is in terms of hydronium, but rather than using hydronium, let's just use H+. I need acid, permanganate and acid. Why do I need acid? In fact, I need 8 H pluses for this. And can somebody tell me the reason I'd need 8 H pluses? Well, the H plus doesn't change in terms of oxidation state. Basically, I need the H pluses because this is something I talked about. This is why I say maybe it's not a bad idea to start reviewing for the final, because we talked about the pattern here. When you look at the redox chart, you notice certain things require H plus. H plus, H plus, H plus. Those things that require H plus all have something in common. What do they all have in common? Let me find a different one with H plus rather than hydronium. This one says H plus. What do they all have in common? They all form water. This one, do I want to use this one? This one has one additional complication. I don't want to talk about it right now. Find another one. Okay, this is good. Draw the E here. So permanganate is a very strong oxidizing agent. It's really going to want electrons here. And so that's what's going to pull the electrons through the wire. And so this permanganate, well, this permanganate has to be in contact with the wire. So should we just dip the wire into the permanganate solution and let the permanganate pull the electrons off the wire? Well, it depends on what the wire is made out of. Typically, we don't just dip the wire in there. Usually we put we call a electrode in here. So this would be the cathode here. And so the permanganate is going to pull the electrons off the cathode. But we want it to pull the electrons through the wire. We don't want it to take it directly from the cathode. So if I put a piece of zinc in here, do you know what's going to happen? The permanganate will just take the electrons directly from the zinc electrode. And so what we need here is we need something called an inert electrode. An inert electrode means that the permanganate is going to try to pull the electrons off this electrode, but it can't. And so it's going to have to pull the electrons off something else, and that something else is located in the other beaker, which we call a half cell. And so over here, it's got to pull it. And so what we need is an inert electrode. So what would survive being attacked by permanganate? Let's see, will gold survive? And so the way we read these charts is like this. Permanganate, being an oxidizer, will oxidize everything below water here. And so below Mn2+. So any reducing agent stronger than Mn2+ will be oxidized. And so, for example, if we use zinc, for sure permanganate will oxidize zinc. But not only zinc, it'll oxidize iron, cadmium, nickel, lead, even copper. Copper was our inert electrode before, but copper will not be an inert electrode here, because if we make this out of copper metal, the permanganate in H+ will attack the copper metal directly, and the electrons will be transferred through here, not through this wire. And so we continue. Silver, will silver work? No. We need something above here, but when I look above here, I run out of, does water conduct electricity? No, nor does fluoride. I can't make an electrode out of fluoride, can I? And so I need something that conducts electricity. And so, you know what, I'm going to go back to this other table here. Let's see if this table has more. Actually, that's the table we're looking at. Okay, here, this one will work. So here's my permanganate here. Actually, this has two permanganates here. I'm going to use this permanganate reaction. There's a reason for this. We'll talk about it later. Oh, no, this is not permanganate. This is MnO2. This is permanganate here. Shoot. Will gold work? No. Gold will not work because gold is a stronger reducing agent. So if permanganate oxidizes gold, we form gold 3. And so gold 3 is a weaker oxidizer, so we're going from stronger oxidizer. Actually, no. Is that right? Stronger to weaker. So if permanganate oxidizes gold, we form gold 3. Yeah, so we're going from stronger oxidizer to weaker oxidizer, meaning gold will be attacked. So gold won't work. We're running out of choices. Lead for sure is going to be attacked because lead is way down here. And so permanganate will react. This is a quick way to determine what permanganate will react with. It'll react with everything here. And so what's harder to oxidize than gold? Platinum. Platinum's not on this chart, but platinum is in Appendix D, so platinum would work. We're running out of choices. And so it looks like the only thing that's going to be inert here will be platinum. So we'll leave this at platinum. And so what's going to happen is the permanganate and the H+ are going to try to take the electrons from platinum. But platinum's up here. If platinum's up here, what happens is permanganate oxidizes platinum to form a new oxidizing agent. The new oxidizing agent is actually going to be a stronger oxidizer than permanganate, which is okay. And so permanganate will not be able to oxidize platinum.
but it's going to try to pull the electrons off platinum, which in turn is going to try to pull the electrons off the copper wire here. But, you know, we don't have platinum going all the way here. And so what happens is this turns into copper here with an alligator clip, let's say. Let's put a copper alligator clip there. And so we have our platinum attached to copper. Now I know permanganate should oxidize copper. Because if permanganate oxidizes copper, where's copper? Copper's here. We form copper 2+. Copper 2+ is a much weaker oxidizer than permanganate. So we're going from stronger to weaker. And therefore, when permanganate and H+ is pulling on electrons in platinum, platinum in turn is going to try to pull them from copper. And it should be able to pull them from copper. But it doesn't. Why? Well, one thing is the copper has a plastic coating on it. But even with the plastic coating, another thing is, if it were to pull the electrons off the copper metal here, which it should be able to, we would form copper 2+ in air, right? Copper 2+ ions in air versus copper 2+ ions in aqueous solution. Is there an energy difference there? Yeah, copper 2+ in aqueous solution is a lot more stable than copper 2+ in air. And so because we're forming copper 2+ in air, it's not going to pull it off here. And so what in turn is going to happen is the copper is going to start pulling the electrons until there's something it can pull the electrons off of. And that something that the electrons can be pulled off of is called the reducer. And so we need the reducer over here. And so what should we use as the reducer in this? A reaction. Well, any metal, you know, most metals are good reducers except for platinum, gold, you know, the noble metals, but most other metals are pretty good reducers. That is, lithium would be the best, for sure. But lithium is such a powerful reducer that if you put lithium in water, do you know what happens? Explosion. And so we don't want to put any lithium in water. In fact, this is what they say. They say never use water on metal fires. Because, you know, metals are powerful reducers. Water is actually an oxidizer. And so you're mixing oxidizer with a reducer, you're going to get a potential violent reaction. Aluminum, yeah, any metal's good, but let's get some variety in there. Does a reducer have to be a metal? Can a reducer be something else? Like, for example, can a cation be a reducer? That doesn't make sense because cations are positively charged, right? Would a cation actually lose an electron? It's already lost electrons. Is it possible that a cation could be a reducer? Yes or no?
Yes.
Yes. Give me an example of a cation that could actually lose electrons.
Hydrogen.
Hydrogen cation? Okay, let's try it out, you know, structurally. Hydrogen cation loses an electron to form a hydrogen 2+ cation. Does that look okay? Does it look a little bit okay? No? Just a little bit okay. Or is it absolutely not okay? Absolutely not okay. Why? Absolutely not okay. Oh. Absolutely impossible. Yeah, how does it lose something it doesn't have? Right, because a hydrogen atom consists of one electron, one proton. And so a hydrogen atom can lose an electron to form a hydrogen cation. But once it's lost its one electron, it has no more electrons to give away, right? So what is that? Now, think of another cation that can lose electrons. Copper 1. Yeah. copper 1 can lose an electron to go to copper 2. You can see it's this reaction here in the reverse direction. Copper 1 goes to copper 2 plus an electron. So copper 1 could be a reducer. It's a positively charged species. What else? Copper 1 is not that common because it's not that stable. Copper 2 is more stable.
Nickel 3 to 2.
Nickel 2. Nickel 2 versus what? Nickel 3? Nickel 2 is by far the most stable. In fact, most of the compounds in nature are nickel 2. So much so that, you know, there really isn't much nickel 3 out there. And so everything is nickel 2. But there are some, you know, nickel does have variable charge. You know, it's so much so that in Chem 4, they tell you to call nickel a fixed charge cation. There's only one charge on nickel, but in Chem 1b, there are multiple charges, so we'd still call it variable charge, but it's a heavily biased towards nickel 2. And so nickel 2 is not the best. There's another one. Tin 2 is a good one. Tin 2 can lose 2 electrons to form tin 4. So that's good. Tin 2 goes to tin 4. Do you see it? Tin 2 goes to tin 4 plus 2 electrons. So tin 2 is one of the most common ones, cations that are reducing agents. And give me another extremely common one. Lead 2 to lead 4 is not that common.
Chromium?
Hmm?
Chromium?
Chromium what to chromium what?
Chromium 3, chromium 6.
Okay, that one isn't as common because this one is going to involve a more complicated reaction. Chromium 3 plus 7 waters, 2 chromium 3s plus 7 waters gives us a dichromate. And so what I wanted was, I just wanted a simple cation, monatomic cation that gives up electrons. But it does, you're right, chromium 3 does and can. But I'm looking for something that just has only the cation on the right side, no water. Because if we include chromium 3, we got to include manganese 2 plus, some of these more complicated ones. I want something that's just simple, like tin 2 ion goes to tin 4 ion. The other one you should know is iron. What is it? Iron 2 goes to iron 3. So the two most common ones are iron 2 is a good reducing agent, and tin 2 is an even better reducing agent. And so which one should we use? Just to mix things up.
Common one.
Well, the common one, iron 2. Let's put it up. So we'll put some iron 2 in here, maybe some sulfate. So iron 2 sulfate is something we have. And so what's going to happen is the permanganate and the H plus are going to pull electrons from the platinum. Platinum is not going to lose them. Platinum is going to pull it from the copper. Copper is not going to lose it. Copper is going to pull it from the iron 2 plus, and the iron 2 plus will lose it. But is it okay to put copper in here? We don't want it to react, right? And so over here we want an inert electrode. At the anode we also want this inert. Because this is different. In the last cell we did, in the last battery we did, we had zinc as our anode. And zinc was both our anode and our reducer. In this case, the electrode and the reducer are different. And so the electrode is just going to take the electrons from the iron 2 to pass them along to permanganate. And so what kind of, well, I need something that conducts electricity. I want something that conducts electricity that won't react with iron 2. So what choices do I have? Silver, no problem. Silver is good. Would copper work? Okay, now look. Would copper work? Copper again. Here, here's copper. So this is what we do now. Iron 2 will oxidize any reducing agent more powerful than iron. And so iron 2, could we use chromium metal? No. Could we use zinc? If I put zinc in here, the iron 2 would attack it directly and take electrons from it. Because iron 2, you have to be careful, because when we think about reactivity for iron 2, all of a sudden, we have to think in two ways. It has to be inert in two ways. Whereas permanganate doesn't. Permanganate, the only thing it can do is be an oxidizer. Iron 2 can be both an oxidizer and a reducer. And so if iron 2 acts as an oxidizer, we got to watch out. If iron 2 reacts as an oxidizer, we can't use chromium, we can't use zinc, we can't use manganese, aluminum, beryllium, magnesium, sodium. If iron 2 is an oxide, we could use cadmium. This is lead with sulfate. I don't want to talk about that. We could use nickel. We could use lead. We could use copper, silver, gold. All those would be considered inert. And so here, iron, which one do you want to use? Nickel?
Nickel.
Nickel? Or copper? And so we could use something like nickel. But iron 2, we have to also worry, because not only is iron 2 an oxidizer, it's also a reducer. And so if iron 2 acts as a reducer, then what can iron 2 react with as a reducer? And so here's iron 2 as a reducer. Iron 2 gives up an electron to form iron 3. And so iron 2 as a reducer will react with any oxidizer stronger than iron 3. And so that means that iron 2 will react with silver ions, mercury 1, mercury 2, nitrate, bromine, oxygen, etc. But would any of these make a good electrode? No. Iron 2 will not react with any of these, because these oxidizers are weaker than iron 3. Does that make sense? You could do this in a circular way too. If iron 2 reacts with iodine, we form iodide, and then compare. Iodide is stronger reducer than iron 2. Therefore, we're going from a weaker reducer to a stronger reducer, which is no reaction. Does that make sense? And so this is how you can use the chart. But when you use the chart in this way, you got to be comfortable with redox reactions like we're doing in the first week. And then you can just do it in your head, you know, on the chart. The more familiar you get with it. Well, anyway, nickel's fine. It's not going to react with iron 2. Then we got to check the reactivity of sulfate. What is sulfate? Actually, we should use the chart in our book. Is sulfate very reactive? Look on the chart there. Are you familiar with the chart in our class? Yeah, sulfate can react. This is from chapter 20 of the book. Here. As an oxidizer, but we're missing something. We have sulfate, but we don't have H+. And we need the H+ to form water. Otherwise, we're going to end up with oxide. So and so it's not going to react. Yeah. So it won't attack. It should attack the nickel, but let's see, would it? Sulfate and acid attach the nickel. And so we'd look for this. Sulfate and acid will attack any reducing agent stronger than SO2. So nickel's not here. Nickel would be up here, so we're okay. All right. So what's going to happen now is the permanganate and the H+ are going to pull the electrons, and eventually it's going to pull the electrons off nickel. I didn't check that, did I? Because this is trying to pull electrons. And I just looked at reactivity here, but the permanganate and the H+ are could they pull the electrons off the nickel? I want the electrons to come from iron 2 because I just want to mix things up. And so I want to make sure that this electrode is inert because I don't want this electrode to react. Electrons are going to come from the iron 2. Is permanganate and H+ capable of oxidizing nickel? Look at this chart and you tell me. Just raise it one more click higher. Is permanganate and H+ capable, in other words, can permanganate and H+ pull electrons off nickel? Yes. How did you figure that out? This permanganate and H+ can oxidize any reducing agent stronger than manganese 2 and 1. And so we already saw that permanganate and H+ can oxidize gold. When permanganate and H+ oxidizes gold, we form gold 3. We compare the two oxidizing agents. Permanganate is stronger than gold 3. Therefore, we get reaction. Permanganate can oxidize chloride to form chlorine. Chlorine, the weaker oxidizer. Permanganate stronger. We're going from stronger to weaker. That's reaction. As we go along, permanganate and H+ can oxidize any reducing agent stronger than Mn2+, which is all these, including nickel. And so if I set this up, what's going to happen is this is not going to be an inert electrode. This is going to be a reactive electrode. Right? Because the permanganate and H+ are going to just strip electrons off the nickel. The nickel is going to go to nickel 2+ in solution. And so unfortunately, nickel will not work here. What do I need to use here? I would have to use platinum. I need to use platinum, otherwise the electrons are going to be pulled off. Platinum. Even though the platinum is not going to react with anything in here, it'll react with over there. Does that make sense? All right, so what's going to happen here is the iron 2+ is going to collide with the platinum. And when it collides, it's going to feel a tug. Something's trying to pull the electron off the iron 2+. What is trying to pull the electron off the iron 2+? Is the platinum? So iron 2+ collides with the platinum, and it's going to feel a tug. Something's trying to strip it of its electron, one of its electrons.
What is trying to strip the electron off iron 2 plus?
The platinum, the copper wire, the platinum? No, it's going to be the permanganate. Now, the permanganate is going to try to strip it off. Will it succeed? Well, let's take a look. Permanganate in H plus is it capable of oxidizing iron 2 plus? So we have permanganate in H plus oxidizes iron 2 plus to form iron 3 plus, and then compare permanganate in H plus versus iron 3 plus. Well, permanganate in H plus is stronger. Iron 3 plus is weaker, so we're going from stronger to weaker. And so what's going to happen is this iron 2 plus is going to lose an electron to go to iron 3 plus. And that electron is going to be fed into the circuit, the external circuit, and given to permanganate in H plus. Permanganate in H plus are going to take the electrons. And so permanganate plus 8H plus 5 electrons yields Mn2 plus 4 H2Os. And so the permanganate is going to gain the electrons, but over here it gains 5 electrons. Over here it just loses 1 electron, so it's an unbalance. Do you know how we balance these? The way we balance these is by adding up the 2 half reactions. So this is iron 2 plus goes to iron 3 plus an electron by changing the coefficient. And so this one we multiply by 5. This one we just multiply by 1. And so the net reaction is 5 iron 2 pluses plus 1 permanganate plus 8 H pluses. The electrons cancel, so I'm not even going to write those. Yields 5 iron 3 pluses plus Mn2 plus 4 H2O liquid. And so this is the net reaction that's occurring here, but the reaction is happening in 2 separate places. The 2 separate places are this. Over here at the anode, we have the reducer. And when we have the reducer, what kind of reaction is this? This is called a half reaction. This is called is that a reduction half reaction or an oxidation half reaction? This is an oxidation half reaction. So this is our oxidation half reaction here. And then over on the other side, we have our reduction half reaction. And when we combine these two, we get our net redox reaction. And so at the anode, oxidation occurs. Oxidation generates electrons. So we generate the electrons at the anode. They're generated by the oxidizer over here pulling. And those electrons are transferred or pulled towards the oxidizer here. We can measure the force of the pull by measuring we measure the voltage. The voltage is given the symbol E or V. In our book, it's given the symbol E. E stands for electromotive force or potential. EMF. It comes from EMF. Electromotive force. It's a force pulling the electrons through the circuit. There. Now, are we going to get a voltage? Right now, we're just going to get 0 volts. How come? Yeah, we're missing a salt bridge. We need that salt bridge here. So we put a salt bridge in here, and then we get a voltage. The salt bridge is going to consist of inert salt. So tell me what an inert salt that you might use for this particular reaction. NaCl would be good. Because, for example, the chlorides would migrate to the anode. Chloride and iron 2, nothing. Chloride and iron 3, nothing. Chloride and sulfate, nothing. Chloride and platinum, for sure, nothing. And then the sodiums would migrate to the cathode. The sodiums aren't going to react with anything here. Then we're done. Then what we're going to do is we're going to do this under standard conditions. What does it mean under standard conditions? Yeah, we need everything to be all ones. And so that means the iron 2 plus over here, we need to make sure is 1 molar. But not only do we have to have the iron 2 plus at 1 molar, we also have to have what else at 1 molar? The SO4? It's going to be 1 molar. But there's something else that has to be 1 molar. It's weird because what are we making here? We're making iron 3 plus. But to do this under standard conditions, the iron 3 plus also has to be at 1 molar. Why? We're making it. And so why do we have to add it? Well, the reason we have to add it is because we just want one simple table. And that simple table is going to be under standard conditions. Otherwise, we'd have to have a whole bunch of tables, right, with non-standard values. So this is why we add it. Well, the same thing is going to happen over here. To do this under standard conditions, the permanganate has to be 1 molar. What about the H plus? If I look at the ratio here, I got 1 permanganate and H pluses. So the permanganate must be 1 molar. Does that mean the H plus is 8 molar? No. Do you know what the H plus is going to be under standard conditions? 1 molar. Now, how can that be? Well, easily. You've done this many times before. When you put in the initial conditions, do the initial conditions have to match the ratios in the equation above, in the ICE table? When you filled out the ICE table, did you, let's say it was 1A plus 3B, did you put 1 molar for A and then 3 molar for B? No, you just put whatever molarity you want. What this 1 to 8 ratio tells us is what's going to be the limiting reagent. What's going to be the limiting reagent? The H plus. Because if I have 1 molar permanganate, I really need 8 molar H plus, but I don't have it. I only have 1 molar H plus. And so this ratio just tells me the ratio in which they react. They don't tell me the initial ratio present. It's easy to make. All I do is sprinkle some potassium permanganate in here and pour some HCl. And I get the potassium permanganate at 1 molar and the HCl at 1 molar, and then I got everything at 1 molar, right? But this is under standard conditions. So tell me what else I need in this beaker to make it standard. There's something missing in this beaker that needs to be there at 1 molar. What is it? Well, the water, yeah. Water is a pure liquid. Yes, sodium or potassium, but let's ignore that. There's something else that's critical, not a spectator. You know, like this sulfate's a spectator, so I really don't care what its concentration is. It's not really going to participate.
Manganese 2 plus.
Yes. Even though I'm making manganese 2 plus, in order to do this under standard conditions, I have to sprinkle in manganese 2 chloride or something like that. You know, which is a hassle because I don't want to. It's a product. But to make sure that this is under standard conditions, I have to add in product here to begin with. And make sure that is 1 molar. Now this battery is under standard conditions. Why do I care about standard conditions? Why I care about standard conditions is because it gives us like a way to compare, you know, different batteries. Because different batteries are going to generate different voltages or potentials. Voltage and potential are the same thing. And so do you know under standard conditions what kind of voltage I can, you know, this is the great thing about standard conditions is I can figure out the voltage here without measuring it. You know, let me figure out the voltage here. I'll tell you what the voltage is going to be. 0.46 volts. That's why we do things under standard conditions. That was easy.
Are you not using the Mn2 plus above?
Oh.
Isn't it 1.51?
Yeah. Not so easy. Not so easy. I'm not used to this particular table. Yeah, 151. 0.74 volts. Well, that was easy. 0.74 volts. You know, and so this is the utility of doing it under standard conditions, because if you made, like, say, if you made this 0, that's going to change the voltage, right? We don't want to, even though we don't want to add product in there, if we don't have the product in there, that changes the voltage, and it makes it not so easy to predict. Because what we're going to do is we're going to just figure out the standard potential and then do a correction to the standard for non-standard conditions. Just like delta G. The delta G non-standard, we calculated the standard delta G and then applied the correction, RT Q, to that, right? Well, the same thing's going to happen here. We just figure out the standard. Well, this is under standard conditions. Now if I go under non-standard conditions, I'm just going to do simply a correction to my standard. And so this is what we call E naught of the cell, or E naught of the reaction. That is the standard cell potential, or the standard cell voltage, or the standard reaction potential, or the standard reaction voltage. And the standard voltage is going to be made up of two things. This voltage is a composite. When we think about this cell here, there's actually a tug of war going on in this cell. You know, one side versus the other side. You know, they're pulling electrons here. And so there's a tug of war between iron 2 and permanganate. You know, who's going to pull the electrons? And so, or iron 3. And so when we look at this tug of war here, we see that the net result is permanganate 1. Permanganate 1 by 0.74 volts. And so when we're thinking about individual strengths, you know, how strong is permanganate H plus versus Fe2 plus? Or if we're comparing oxidizing agents, how strong is permanganate H plus versus Fe3 plus? Because basically we're going to have Fe3 plus, which is an oxidizer, can take electrons, and we have permanganate and H plus, which is an oxidizer, can take electrons. And so who's stronger? Well, permanganate and H plus is stronger, right? And it's stronger by 0.74 volts. And so what we want to do now is this. You know, that's the relative strength difference. You know, the relative strength difference is this is stronger than this. Therefore, the electrons get pulled left to right. This is tug of war. And so this side's weaker, the electrons, or the rope gets pulled this way. Well, now what I want to do is, you know, I want to know their individual strength. You know, for example, how strong is permanganate and H plus on an absolute scale? And how strong is iron 3 plus on an absolute scale? That way I can rank everybody and compare everybody, right? And so what this is going to equal here is it's going to equal the what we call the potential for the cathode plus the potential for the anode. Although I'm mixing it up a little bit here. In other words, what happens at the cathode? Reduction. And so it consists of the reduction potential plus the, at the anode, oxidation occurs, the oxidation potential. And so the reduction potential, that's what's pulling the electrons over here. And so what must be pulling the electrons is a reduction potential greater than 0.74 volts, less than 0.74 volts, or equal to 0.74 volts. how hard is the permanganate in H plus pulling on the electron? Is it pulling with 0.74 volts electromotive force? Or greater than? It's got to be greater. Does everybody see that this has got to be pulling with greater force because there's resistance back here? And so what must be happening is this might be pulling with 1 volt, and back over here, this might be pulling with 0.24 volts. But it's pulling the electrons the opposite direction. When you pull the electrons the opposite direction, we change the sign. And so it's negative 0.24 volts, right? And so we end up with 1 minus 0.24, that gives us 0.26, sorry. 1 minus 0.26 gives us 0.74 volts, right? And so what we want to know is we want to know the individual strengths, not the combined. Now, does that sound about right? 1 volt plus a minus 0.24 volts, 26 volts gives us 0.74 volts. Or maybe it's pulling with 2 volts. If it's pulling with 2 volts, then this might be resisting by 1.26 volts. Does that sound about right? Or how many volts of that 0.74 is because of this, and how many volts is because of this? That's what we want to know. And so what we have here is a scenario where we have 2 unknowns. I don't know what voltage this is and what voltage this is. I have 2 unknowns and 1 equation. And so what do I need? If you have 2 unknowns, you need 2 equations. So I've got 1 equation there. Can you think of a second equation that'll allow me to solve for the individual voltages? In other words, the individual potentials. In other words, this is what I have. I know 0.74 volts is equal to x plus y. I want to figure out what x is, and I want to figure out what y is. I could take a guess. So I could guess that x is 1.0 volts and y is minus 0.26 volts. And that would give me 0.74 volts. And so is that right? It works. Is it right? No. It works, but so do a whole bunch of other things, other combinations. And so I need a unique value. And so I need a second equation. Can you think of a second equation for this to let me solve for x or y? There is no second equation for this. If there's no second equation for this, then it's impossible. We call it impossible to solve, right? How can you solve this when we don't have a second equation? This is impossible to solve. But we solve it anyway. Done it before. Do you remember when you saw 2 unknowns with 1 equation? You saw it in Chem 1A, Chapter 7. You saw it again in Chapter 19. 2 unknowns, 1 equation. Impossible to solve, but we solved it. How did we solve it? And why does it work?
Are we going to set 0.74 equal to 0?
It's close. You're close. You're getting warm, but we don't set 0.74 equal to 0. 0.74 is not equal to 0.
Arbitrary pick x and y equals 0?
Yes. Do you remember how we solved it before? We did an arbitrary. We picked one of these and called it 0. That's how we solved it. And so which one do you want to pick? Do you want to pick the strength of permanganate and call it 0? Probably not. Let's just call iron. 3, 0. And so if we call this one 0 volts, then the strength of permanganate is 0.74 volts. But isn't that just as ridiculous as doing this? Just go ahead, I signed this, 1 volt for this minus 0.26 volts for this. It's just as ridiculous as this, but this would have worked. This would have worked and this would have worked. Why? It would have worked because of this. You cannot have oxidation without reduction. You must have both of these. The same thing happens. Can you have a bottle of cations without anions? I just want the cations, leave the anions out. Is that possible? Impossible. Just like, can you have an oxidation reaction without reduction? No, impossible. And so what happens is, one of these is going to be, actually both of these are hugely narrow, right? One of these is going to be way too small, the other is going to be way too big, but when you add them up, the errors cancel. We saw the exact same thing. Where did we see the exact same thing? We saw it in Chem 1A. You remember where we arbitrarily set something to 0 in Chem 1A in order to solve a 2 unknown, 1 equation problem? Had to do with delta H of formation of HCl. This is like 1 page in chapter 7 that talks about delta H of formation of HCl. We arbitrarily set delta H of formation of H plus as, I talked about this chapter 19.2, because we're using appendix D. And so we arbitrarily set the delta H of formation for H plus as 0, but it's impossible. Let me just refresh your memory. H2 gas goes to 2H plus, delta H of formation is 0. There's no energy involved in converting hydrogen gas to hydrogen ions. Impossible, right? This is impossible because you got to break the bond and then you got to ionize it. And then you got to dissolve it in water. There's going to be energy changes here. But we arbitrarily set it to 0, and where did all that energy go? Into, well, somebody, who asked me about the final exam? Did somebody ask me about the final exam yesterday?
We talked about it 2 days ago.
Didn't we talk about the final exam 2 days ago? A little bit? And so this is what you want to do in preparation. You want to go back and review. We set this one to 0, and we gave all the energy to chloride. And so chloride came out to minus 167 kilojoules. Hydrogen ions came out to 0, and so delta H of formation of HClAq is minus 167 kilojoules. So we see the exact same thing. Okay, that's where we saw it in Chem 1A. Where did we see it in Chem 1B? 2 places we saw it in Chem 1B so far. This will be the third. The first place we saw it in Chem 1B dealt with the well, I guess we haven't tested. Did I test you on this already? Oh no, I haven't tested you on this yet. So I probably haven't really reviewed it. Okay. The first time we saw an arbitrary 0 in Chem 1B was when we were talking about,
Enthalpy?
not enthalpy, but it starts with an E.
Entropy?
Entropy. When we're talking about entropy, there are 2 entropies. An absolute 0, which is called the third law of thermodynamics, and an arbitrary 0. What was the arbitrary 0 in entropy related to?
The same thing in appendix D.
Yes, exact same thing from Appendix D. I told you, you know, if you want to use Appendix D, you should know these things. Well, anyway, I heard the new version of the MCAT. You know, I told you about my friend. My friend, did I tell you about my friend who was studying for the MCAT?
No.
You know, because I'm a chem major, so my friend who's bio major wanted me to help him review for the chemistry part, the general chemistry part of the MCAT. And so I said, sure, no problem. So I sat with him, and then we started reviewing, and I realized he forgot everything. I mean, everything. He didn't know anything. Everything was completely. And so then I thought, oh, no way are you going to be able to get this in time for the MCAT this year. But he still took it, and he didn't do so well. And so he ended up taking a year off just to review all the stuff he had forgotten, you know? But you think it's so easy to forget if you don't ever use it or if you don't ever look at it again. He could afford to take a year off, you know, and do nothing but study. He didn't work or do anything. He just studied for that year. He, after, I don't know, well, a year off wasn't enough because the following year he didn't make it either. And he ended up spending 4 years reviewing and then finally made it into an American medical school in the Caribbean, which is very expensive. So if you could afford it and you make the bare minimum, you can get into, you know, that was kind of the last resort medical school, but he made it, which is a private medical school.
How old is he?
He's, at the time, you know, he was probably, he got into medical school in his 30s, probably, early 30s. But I've heard people getting into medical school in their 40s, you know. It just depends on what they're looking for. They might be looking for certain types of life experiences and that type of stuff. And so one thing is he never gave up, you know, that shows quite a bit of persistence. And he eventually, I mean, that was his dream to get into medical school since he was an elementary student. So he made it, which is good. I don't, you know what though, I lost contact. And so I don't know if he actually completed medical school because I have other friends who dropped out of medical school. Actually, I have two friends that dropped out of medical school. It's too intense.
In what year?
One dropped out
First year,
second year, and then started work for a pharmaceutical company as a salesperson, and really actually likes it. I found that they are much better suited to be a pharmaceutical sales rep than MD. And the other one, it was early, but I think there were other, you know, other reasons. The one that dropped out had a really great memory, you know, and he said he never had to take notes. He never had to take notes. He never took notes because he remembered it. But then when he got into medical school, he found out that, boy, he didn't remember it. And he ended up failing out of medical school. But he wouldn't change. It's kind of weird that he didn't change, but his study habits and at least take some notes or something, try to remember. But he was so... But anyway, you know, little stuff is easy to forget. So when you're doing the final, now's the time to start. The whole point of this is, now's the time to start reviewing for the final. We talked about it 2 days ago, but have you started reviewing? And what's the process for reviewing for the final? The process for reviewing the final is just flip back. You know, by the 5th time you've heard about this, you know, it's pretty well set in your memory. If you've only heard it once, you know, like in Chem 1A, you heard it once. Okay, delta H formation has an arbitrary zero. The arbitrary zero is H plus, right? Then it's a lot harder. This was the same problem he had. You know, if you're ever thinking about doing something like the MCAT, you know, you got to stay up on the material and it's not hard. You just have a regular time where you go back through and just review. It is tough, tedious.
But anyway, what was the first time we heard about the arbitrary zero in Chem 1B? It starts with E. It's entropy. Tell me, what is the arbitrary zero in entropy? We have an absolute zero called the third law. What's the third law of thermodynamics? Entropy of a perfect crystal is zero. Can we go below zero? No, unless we're going below an arbitrary zero. So what was the arbitrary zero? You could use HCl as the example. It's the ways of arranging, but the ways of arranging, the Boltzmann equation does not apply. You know, it does not apply to the arbitrary zero. The Boltzmann equation only applies to the absolute zero. And so if you only have one way of arranging it, then the absolute entropy is zero. It's funny because we have absolute arbitrary entropies. You know, absolute has two different meanings. That.